Hello everyone, I'm Rohan Rao, data scientist and Kaggle Grandmaster from H2O.ai. I'll be talking about our team's second place solution from the Great Energy Predictor 3 machine learning competition that was held on Kaggle. The primary goal is to understand the various processes and key decisions that were taken by our team to come up with our final solution and how it can be reproduced in a productionized environment. I will also talk about some of the applications of how these models can be used in environmental performance analysis and some very interesting and novel techniques that even we as experienced data scientists got to learn and explore as part of this dataset and competition. Our team consisted of 4 members. We have Oleg and Anton from Germany, Yangwan from China, and myself, Rohan, from India. All of us currently work in the data science and machine learning space in our respective companies and countries. So, the basic agenda is to cover a brief background of our team. Our team was called Chaos in the competition. Then, a quick overview and summary of our solution, along with specific and granular details on the key aspects that led to our final solution, and finally how it can be productionized and what were the key takeaways from the competition and the solutions. So none of us have any prior experience in the energy domain, but we have a strong background in mathematics, statistics, and technology. We have worked on various different Kaggle datasets and competitions across multiple industries and domains. So our team had 1 Kaggle Grandmaster, 1 Kaggle Master, and 2 Kaggle experts. So coming to the dataset and our solution, so this is an overall view of what our solution looks like. So the dataset consisted of the meter readings from 16 different sites from 0 to 15. Most of our initial analysis, exploration, and work that was done, we broke down the data into different sites. So we had a data set for every site and we analyzed, explored, and optimized the performance for each site individually. So while there were 16 sites in total, unfortunately 5 of the sites, the ones that are present on the right, which is site 0, 1, 2, 4, and 15, the true labels of the meter readings were publicly available from various sources, and this data was scraped and made available to everyone in the competition. Hence, we did not use these 5 sites for modeling, but we used it for validation and our final submission. So coming to the remaining 11 sites, our basic flow consisted of 4 major steps. So the first is pre-processing, where we worked on cleaning the data, identifying and removing the outliers, and doing some basic feature engineering. Then came the modeling part, where we plugged in the cleaned datasets into these different models. So XGB is the XGBoost model, LGBM is the LightGBM model, CB is the CatBoost model, and FFNN is the feed-forward neural network models. So the first 3 are tree and boosting based models, whereas the last one, which is the FFNN, is a neural network based model. From the model's outputs, we applied a post-processing factor, which I will describe a little later in the slides. And finally, after the post-processing was applied, where the outputted probabilities, the outputted scores had a reducing factor, We then ensembled the outputs from various different models using a weighted average technique. The post-processing and the ensembling aspects were also validated using the leaked dataset just to confirm that they were optimal. So let's look at each of these aspects in detail. First is the pre-processing. So the pre-processing, data cleaning and outlier detection formed the main crux of our solution. So the primary insight that we've got was there were a lot of zero valued observations in the data, and they seem to be outliers. They could be due to various different reasons. They could be faulty meter readings, there could be some data issues, it could be an aggregation issue, and so on. But what we found was identifying and removing these observations from the dataset significantly helped the stability and performance of the model. We also did a percentile based outlier detection where the bottom 2% of values or the top 3% of values were excluded from the data. So all this analysis and outlier detection and removal was done for every site individually. In terms of the target variable on which the model was built, it was the meter readings of the 4 meters, and instead of using the raw values, we used a log transformed value for the model. The feature engineering aspect of our solution is not very extensive. What we found was it did not add significant value and performance to our solution. Our final models used only about 25 to 30 features, and a majority of them were just the raw variables that were available from the dataset. So if you look at the top few features, you have building ID, you have hour of the day, you have the square feet of the building, the month of the year it was built, the day of the month, and so on. So most of these features are the raw features that were available, and any additional feature engineering that we tried did not help in improving the model performance. The modeling piece was our second major component. So we built models at various different levels of data and we combined different models. So we built models for every site and meter combination, every building and meter combination, as well as every primary use and meter combination. The models that were used, as I described earlier, are the boosting models like GBM, XGBoost, and CatBoost, along with feed-forward neural networks. So the feed-forward neural network models were built only for the electricity meter. We found that we were not able to get good architectures of the neural network for the other 3 meters, which is steamed water, which is steam, chilled water, and hot water. The parameter optimization and tuning was based on a 5-fold cross-validation that we had set up based on month. So we divided the dataset into 5 folds and we used those folds to validate our hyperparameters, weights, and different aspects of our model. We also double checked the final weights and the parameters on the leaked sites data just to ensure they were optimal and the best. So the actual meter readings did not show any significant trend or change over time, and hence we did not structure it as a time series problem. It did have some strong seasonality patterns where the summer months showed a different distribution compared to winter months. Some of the sites which were in the educational institutes were related to when courses and semesters were held versus when there were vacations, and so on. Due to this, we set up our cross validation on month and we use this for all our tuning and optimization. Then came the post-processing bit. So when we remove the zero value observations from our training dataset, we artificially increase the mean value of the meter readings. Now, because of this, the model's predictions are also artificially higher than what it should be. And hence, it became important to add a post-processing factor of less than 1 to the model's predictions to rescale it back to its original mean. So we tried values between zero point 0.8 and 0.99. What we found was different models optimized different factors based on our cross-validation scores. But most of our models ended up with a factor of between zero point 0.8 and 0.85. Finally, we had to combine all these predictions from various models. So we used a weighted average for different sites based on our 5-fold cross-validation scores. So we broke it down into two major parts. One was for the electricity meter because we had the feed-forward neural network predictions only for electricity. So the bulk of our predictions came from the light GBM backed models, which was 50%, and the other half was split amongst XGBoost, CatBoost, and a small percentage was given for the feed-forward neural network. Similarly, for the other meters, it's the same proportion, except that the 5% from the neural networks went to the CatBoost models. So this was our progression along the timeline of the competition. So the two bars show our scores on the public leaderboard and private leaderboard, and lower scores imply a better model performance. So if you look at the significant drops, so the drop at our submission number 22 was primarily because of outlier detection and data cleaning. We had another drop at number 76, which was when we did ensembling of our various different models. And finally, we had a good drop at submission number 112, 113, where we did another final big ensemble with different public kernels that used light GBM models. So our complete solution runs in about 48 hours on a 64 GB RAM server with 16 cores. So these were the specifications of the servers we were using for the competition. But if our solution needs to be productionized, we highly recommend to only productionize the light GBM ensemble with all the data pre-processing. The primary reason for this is because the light GBM ensemble runs in about 10 hours only, which is about 1/4 the time, and it gives almost the same score. It is only marginally worse. Also, by using a GPU, the training time for a model can be increased or can be reduced by about 30%. So we estimate that if it is run on GPUs, it can run in about 7 to 8 hours. And finally, the scoring aspect of it. Once the models are built, when it is used in production, what is most important is what is the latency of scoring. So in order to get the predictions of, let's say, the next month's data in the future, it only takes a few seconds. So these are our key takeaways from this competition. So we found that outlier detection and identifying and removing it from the data was the most important aspect. Secondly, we dissected the data for every site and meter, and hence we were able to optimize the models for each of the sites. Using time-based features like hour and month helped capture seasonality and helped coming up with a stable cross-validation framework. Ensembling a lot of different models helped increase the stability of the models and reduced the variance of the predictions. It also gave a low scoring latency when you use only the light GBM models. In the future, I think adding more raw features for these sites or buildings can help in improving the performance, since we found that most of these variables are quite predictive, and doubling down and trying to get more of this data can be very useful and valuable. So that's about our overall solution. We quite enjoyed working on this competition, and we are looking forward to see how this can actually be used, and just looking forward to your feedback and comments. Thank you.